Pre-calculus class. Today we are going to talk about logarithms. Logarithms are a very useful tool in a mathematician's toolbox. There are a lot of different functions that can be modeled using logarithms. There are a lot of different functions that can be modeled using exponentials, and we use logarithms then to help us solve problems involving those exponential functions. Right now in real world, you might have seen a lot of different graphs of the coronavirus data that have used a logarithmic scale on the y-axis because that's often useful to show that exponential growth. If something looks like a linear function, if you have a logarithmic scale on the y-axis, then that shows that something is growing exponentially. So there's a lot of different uses for logs. We are going to look at kind of 4 different ways to use logarithms right now. So first thing we're going to do is just learn what they are and how they work, how we work with them. Yeah, a logarithm is kind of a function. You can also just think of like a logarithm is an exponent, and we'll talk about what that means. Logs have some special properties, so the second thing we're going to do is learn some of those special properties of logs that help us do some math involving logarithms. Third, we're going to solve equations involving logs. So sometimes that may be a logarithmic function, and we're trying to solve for like something on the inside of a log. Other times it'll be solving exponential functions, and we use logs to solve those types of equations. And then the last thing we are going to do is find logarithmic functions through 2 points, just like we did with the powers, exponentials, and linear functions in the last unit. So first off, what is a logarithm? One of the most common ones that we use is something called a base 10 logarithm. The logarithm of a number, the base 10 logarithm of a number, is the exponent in the power of 10 that would give you that number as an answer. So right away we see a logarithm really is an exponent, right? If I write this, we have the log of, I gotta get my pen working here, the logarithm of some number is a different number, and that number is the exponent in the power of 10 that would give me the original number x as my answer. These two things are synonymous, right? Like we use them interchangeably. One is, we call this logarithmic form on the left. On the right, we have this exponential form. But the whole idea is like a logarithm is a function. I put in some number into that function, and what comes out is the exponent in the power of 10 that would give me that original input, right? So you can see too, logs kind of, they're almost the inverses of exponential functions, right? Like here, my input is a number, and what comes out is this exponent. For an exponential function, my input is the exponent, and what comes out is this number, right? So we'll use that a lot. So let's do some examples, see how we work with this. So first example, just evaluate the log of 51,000 and show what that answer means. So to evaluate that, we would need a calculator, and I'm going to rely on Desmos for a lot of this. So I've got a Desmos calculator embedded in over here. Let's shrink this out a little bit. Right. If you go into that little keyboard button down at the bottom left corner of Desmos, go over to functions, this functions button here, and in the miscellaneous section, they have these different, these 3 buttons are all really logs. This is the log button that we're using for now. If I wanted to evaluate what is the log of 51,000, I get 4.70757, right? Plug that into my calculator, I get the log of 51,000. It's 4.70757, and so on, right? And so to show what that answer means, right? Well, that answer, that output, the 4.70757, that is the y value in my equation up here. It's the exponent in the power of 10 that would give me 51,000 as an answer. So another way to write this, again, this is synonymous with saying that 10 to the power of 4.70757 ... is equal to 51,000. 51,000. It found that exponent in the power of 10 that would give me that as an answer. And we can check that. Right? I can do 10 to the power of 4.70757 and keep going. Right? I get that. Right? 10 to that power gives me 51,000 as my answer. Okay. So let's look at another example. To solve for x, I have 359 equals 10 to the power of x. Right? In this case, I'm looking for that exponent there. Right? So if I'm trying to write this, I'd want to go back up again to this definition of what a logarithm is. Right? A logarithm would be used to find this exponent here. I can use logs basically to rewrite this. If this is true, that's synonymous with saying that the log of 359 is x, right? 10 to the something equals this value. In this case, right up here we had y, now we're using x. They're variables, we can use them interchangeably, right? But I would want to find out like what is that thing, right? I'm looking for the exponent in the power of 10 that would give me 359 as an answer. So again, functions, miscellaneous logs, the log of, I gotta click in the right spot here, 359 gives me 2.555, right? I get x is 2.555 is my exponent in the power of 10 that would give me that. And just again to check, right? What is 10 to the 2.555094, right? I get that that is my answer there, right? Third one here says evaluate the log of 10 to the 3.7, right? We'll put this in here. We have a little, right? This is equal to what? Well, let's rewrite it again using that kind of change over here, right? In this case, I'm in that logarithmic form. So I'm really looking for the output here should be the exponent in the power of 10 that would give me 10 to the 3.7 as an answer. So if I wanted to rewrite this, I'd be saying, right, what is the exponent in the power of 10 that is equal to the argument of this logarithmic function, 10 to the 3.7? Well, 10 to the 3.7 is equal to 10 to the 3.7. My question mark here, right? My question mark, my x, whatever it is 3.7. And is looking for the exponent in the power of 10 that would give me the value 10 to the 3.7. Right? So again, go over here just to check this out. Right? Saying what is the log? You can also type it in there. The log of 10 to the power of 3.7 is 3.7. Right? I can find out, right, like what is 10 to the 3.7 power? It's like 5,011. So if I did the log of 5,011, it gives me 3.7 as my answer. Right? So key idea, logs are exponents, right? It's a function where I take like some number as an argument and it returns the exponent in the power of 10 that would give me that argument back. Right? So we use base 10 logs a lot, and if there's no base written, that's what's assumed. If you just see log of something with nothing else like kind of written in a subscript, it means log base 10. But we can use logs of other bases, right? And so we often do use logs of other bases that are not base 10. So if you see something written like this, log base b of x equals y, that means that again, y, this output of the logarithmic function, is the exponent in the power of, in this case, b. That would give you x as the answer. Right? So if I wrote this, log base b of x is y, that is synonymous with saying, right, y is the exponent in the power of b that would give me x as my answer. These two things are interchangeable. So if I see this form, I can rewrite it like that. And if I see this, I can rewrite it like that. And that's often very useful, again, in solving equations and trying to just wrap your head around different things involving exponential growth or decay. Logs are often very useful in that. So we'll see a couple of examples with this. Right, and these are questions that you'll see on an assessment at the end of next week as well. Right, so something like, write log base 7 of c equals k. This is called logarithmic form. I can rewrite that in exponential form. Right. So in both cases, right, we refer to this b here, right, as my base. Right. When I read this left to right, I read log base b of x equals y. Right. This here, when I have an exponential, b is my base. So I have b is my base, y is my exponent, because logs, the output of logs are exponents, equals this answer. The argument of the logarithmic function is equal to the answer in that exponential equation. Okay. So if I see this here, I have 7 is my base in this logarithmic function, the way I've written it here. If I wanted to change it to exponential form, 7 is going to be my base again, right? 7 will be my base, right? So I have log base 7 of this argument is equal to k. The log is k, and logs are exponents, so I know k is my exponent, right? K is the exponent in the power of 7. That would give me c as an answer. These are interchangeable. This is the exponential form of that. I'm not like solving any equation here, I'm just rewriting this. I'm stating an equivalent expression, an equivalent equation. Right? Down here, it says write this. Here, this is given in exponential form. If I wanted to change that to logarithmic form, right, I have the log base something, right? Log base something of something equals some third thing. I just need to rearrange this. Again, q is my base in the exponential, means q is my base in the logarithmic function as well. The base is always the same. Right. 5 is my exponent, and the outputs of logs are exponents, so my 5 is going to go over here. Z is the answer to the exponential function, so z is the argument of that logarithmic function. Right. All right, and then let's actually do a little bit of math. It says right here, evaluate the log base 3 of 243 and show what that answer means. Right. So I'm looking for the log base 3 of 243 is what? Right. Let's kind of jump the gun and go right to showing what this answer means, right? Saying I'm looking for, this is equivalent to saying 3 to the what is equal to 243. I'm saying 3 to what power is equal to 243. 3 is the base of the log, it's the base of this exponential. I'm trying to find it, right? So it's like, what is that exponent in the power of 3? 243 is the argument of the log function, so it's the answer of that exponential. I'm looking for that exponent. If you don't know it off the top of your head, right? Again, I can use my calculator. So if I go back up here, let's see if I can drag this down without it taking too long. Sure. Right. And kind of zoom in here. Right. Kick out some of these. They have a different change of base function in Desmos as well. Some of the TI calculators will have this, some will not. It's in the number feature of your TI calculator. So if you like have your TI calculator, you click the math button, and like actually it's not in the number, it's in just the math. You scroll all the way down and there might be a log base button in there. I would recommend using Desmos here, because in Desmos, if I just use that function right there, this log base will let you put in a base for something. So I want to do log base 3 of 243 gives me 5, right? I can plug that into my calculator. I get log base 3 of 243, just evaluate that. This is equal to 5, which means that 3 to the 5th is 243. Right? So 3 times 3 is 9, times 3 again is 27, 81, 3 5 times would be 243, 3 to the 5th is 243. Right? So if the log base 3 of 243 is 5, means that 3 to the 5th gives me 243 as your answer. There's a few different special bases. We already talked about the one way up here, right, when we just introduced logs. The normal one, and if you just see look at the log button in Desmos, the log button on your calculator, that means the log base 10, right? This is always returning the exponent in the power of 10. That would give you this input as your answer, right? Another special base that we often see is this, and your calculator will have this button as well, an ln button. Desmos has this button. If I go to the functions, right above the log is this ln button, right? That is the log base e, where e is this natural number. E, hopefully you've talked about it maybe in Algebra 2 a little bit, but it's kind of like pi, where it's this irrational number that's 2.718281828 ... That doesn't keep repeating there, but it just kind of goes on forever. It's called the natural number. It's also sometimes called Euler's number. A lot of people introduce it in terms of like compounding interest, but it has just tons of other properties related to exponential growth and large numbers. So it's one that we will use a lot in terms, like when we use logarithms. It's a common base of exponential functions, so we use it as a common base for logarithmic functions. If you want to learn a little bit more about it, this is like a 15-minute video here. It really does a pretty concise job of introducing what E is in the first minute or two. But a lot of people there are videos all over the internet that introduce E as this thing relating to compounding interest, but they say, okay, well, that's great. Why do we use it as this like base for everything, right? Why is it the base for all types of exponential functions? The next 13 minutes of this video does a really good job of kind of showing everywhere that this number shows up. It is a very, very popular number in mathematics. Just like pi, 3.14159, E, a little bit less, but a very powerful number in mathematics. So, all right, there you have the kind of introduction to what logs are. Make sure you watch the next video on what are some of the properties of logs and how we use those to rewrite different logarithmic expressions and eventually use them to solve equations. So, thank you for watching.